So it's time to start with the introduction of virtual vertex. Basically, just to quickly recap, we did this last time, where this is another implementation to check whether there's a CAD between two nodes, um, in a way that it minimizes the amount of control X gates that you need, right? Um, is that true? So yeah, I think so, exactly, because basically you would need, so you just need this two control axes, and then a control set rotation, and then there is, you can do this KK decomposition, which we have to take a look at into later, and that just decomposes into the need of two control NOT gates. Exactly. So this is here. Um, Again, I believe you could also do it. If this also works when you've got, like, why do I have? So why do I have these things as an example here? I believe this also works, if I remember well. Why isn't this working? What did I undo? I undid this. But I'm missing, basically, I'm missing to do the opposite here. The opposite check. And that should be exactly. So that's it basically maximizes those two solutions, but also the 000 and 111. That was 2 videos ago, I think. So yeah. And so, but like, this could also work, right? I mean, wasn't this supposed to, wouldn't this work as well? And then you then you have less of a hassle with decomposing this stuff. I mean, you still have to control nodes, but then you don't have to do all that, right? Because you have a Z rotation, which and then you don't need these stuff in here. Isn't that an auth? Like, I thought that would be one way of doing it. So I'm also getting the same things in here. Like, it doesn't get rid of the problem of the 000 and the 111 solution, because that's caused by the fact that you're using, like, a decomposed, like you're using the phase encoding technique. But then that should kind of work as well. And it's, I mean, you don't need to do that. You don't need to decompose it this way. I don't know. Maybe maybe I'm missing some detail in here. But let's stick to the way the paper implements it, because then they introduce the notion of the virtual vertex, which is the one that I want to take a look at right now. So okay, so this, now we got it to work. It's just checking. In this case, you need basically my drawing tools are not working. Why? Give me a second. I'll have to figure it out. For some reason, my drawing tools do not seem to work. Anyway, so these two blocks in here basically check that there's whether there's like a CAD between those two qubits. So here now let's take a look at the vertex, virtual vertex technique, because the idea here is that you're think the output, so the way they put it is, the output of the approach in section 3 has redundancy due to the symmetry of the problem. In order to eliminate this and double the solution space in a given number of qubits, we introduce a virtual vertex whose state is fixed at 0 sub v. The oracle for the edge connected to this virtual vertex can be replaced by a single qubit operation on the other vertex. In order to reduce the number of control X gates in the oracle part, it is effective to visualize the highest degree vertex. For example, when when the given graph is K14, we can perform the oracle circuit without using control X gates, as shown in figure 8. Okay. Uh, so let's let's try to understand this a bit more. So, and that's it really. That's the section of the virtual vertex. So to eliminate this and double the solution space in the given number case, we introduce a virtual vertex whose state is fixed. The oracle for the edge connected to this vertex can be replaced by a single qubit operation on the other vertex. So, but still, so oracle to VNA between VNB, VNC, VND. But okay, so I see. I mean, it's still what's the point of having the X gates in here where you can just initialize that to 1, or what's the point here? So okay, so let's try to understand how this works. So this is your, so here we've got the actual superposition, the actual nodes, and then you've got like a the vertex 0v. And so how is this supposed to check the cat between A and B? Well, there's a cat between A and B. Because this essentially what it does is it puts it into 1. It does it controls that rotation. But that's not the point. If we are checking, the cat between A and B, say, right? Trying to understand how this, because here on one side, it just bothers me that the drawing tools don't work. So here on one side, we're trying to figure out, we're trying to say, okay, so if so the way this has the symmetry is because we're trying to, okay, so we're operating at the superposition level. Okay, let me see, maybe with an example, it's gonna make it clear. But I'll just copy that. I'll just copy that so I don't lose these, and then try to. So the idea is we've got another virtual vertex, which I'm gonna put at the very top. Whoa. So which I'm gonna put at the very top. And so now we don't have these things in here. So let's get rid of these. Boom, 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 boom. I'll keep one of those gates. And so what this does is this, and then basically like this again. Yeah, but that gives me a different solution, right? In here, or what's the? Am I just not seeing the? Oh, because this is a different example. So this is the oracle for the edge connected to this virtual vertex can be replaced by a single queued operation on the other vertex in order to reduce the number of control gates in the oracle part. It is effective to visualize the highest degree vertex. For example, when the given graph is K14, we can perform the oracle circle without using CX gates. What was the I forgot what was the K14. Is it the star graph K14? Okay, this. Uh-huh. Uh, Still don't get it. Oh, wait a second. Uh, isn't that what I was? No, no, that's no. So how is this supposed to work on the other vertex? So how is the virtual vertex supposed to help in here? And what is this virtual vertex supposed to do? That's what's not clear to me. The virtual vertex state is fixed at. So the oracle for the edge connected to this virtual vertex replaced by a single queued operation. On the other vertex, yeah, not to reduce the number of control X gates on the oracle part is effective to virtualize. Okay. Now I was reading visualize. Now it's virtualize. Okay. So it's okay. So it's saying in order to reduce the number of control X gates in the oracle part, it is effective to virtualize the highest degree vertex. Okay, so the vertex that has the highest amount of connections is the one that you're gonna virtualize. So you're basically gonna remove it, and then you're just okay, and then so, huh, for example, if we've got the if we've got, man, it just bothers me with the drawing tools. I can't. Give me a second. I gotta fix this. I give up. I can't really fix that. So we'll try to have to figure this out somehow else. So if you've got like the uh yeah, I get it. Okay, so if this, that's why this works. This is example. If you take the highest degree, let's assume in this case K14, right? I mean, it means that there's one vertex that's connected to all of them. It's a star graph. So the highest degree is the one that's connected to all of them, and then that effectively becomes your like you can virtualize it. So this means you don't have to do this two-way thing, because it's always going to be it's always going to be 0. No, I mean, you don't need to do that, because you just need to check whether I mean, it's connected to all of them, so you just need to check whether um, the other qubit is, in this case, a 1. So you're basically initializing it always to 0. Okay, so you're initializing it always to 0, and then you're let me see if I can explain that with this example. So let's assume we're using that, just because I can't draw it right now. Let's assume we're using these this exact here, right? So 0, 1, 2, and so uh, the highest connected one is the node number 1, because it's connected to those two. right? So we're going to virtualize this one. If node number one is the node in the middle, let it be. So let me get rid of this for a second. Uh, let's put this back. How this. How was this? Was this like this? So this was like that. So, but we're gonna virtualize now. I'm just gonna put these things here for a second. Let's get rid of, just let's get rid of everything. So we're gonna virtualize basically, and I'm gonna get rid of absolutely everything. Like, you know what? You know what? I'll just clear all. So we're gonna virtualize the. So usually you would have that, right? So and this is qubit number one. So we're gonna virtualize this one. So this one is gonna basically not be in superposition anymore. And so it's going to be always initialized to 0. And the idea here is that you don't need to check it. You don't need to check it to check it two ways, because you know that between these and these. Let me see. How can I reason that? I feel like I'm. So A, B, C, and D. I'm trying to think. I'm trying to find a clean, a nice way to explain it. So, because I don't even know what I'm not even sure what I think I just have it there. So you're only doing the you're only doing that the check on one in one direction. So you're only doing this and and you're only doing it this way. Right? Does this make sense? Doesn't make much sense. Now, what I'm looking at, I want to take a look at at these things in here. So, but it's still I'm missing. If I virtualize it, I'm actually missing on that superposition, right? Because now I've got this solution that has one cat 60 degrees, this solution that has one cat 60 degrees, and this solution which has two cats like 120 degrees. That's correct. But this solution has also one cat and it's got nothing in there because we haven't brought this into superposition. But maybe okay, maybe what this means is you actually just gotta have that extra as a virtualization, and then simply have like that, right? So, and basically now you want to measure just this. Okay, yeah, I think that's. And of course, if there's any other connections, you still gotta do. So give me a second. So let's check if that's correct. So this has got one cat 60 degrees. This has got no, that's wrong. So this has got two cats. So the phase for the star. All suboracles can be replaced with RZ by assigning the highest degree vertex to the virtual qubit. I don't quite fully get the. I don't quite fully get the way this is supposed to work. I get the Roth idea. Man, it's such a small subsection, and I'm like struggling with that. I get, but how I would implement that? So for the example of the paper, not the star graph here. Um, so I mean, even for the star graph, that doesn't, because you still got that solution, that solution, that solution, but you're still missing. Uh, sorry, what am I doing? Uh, this is this. So, I wanted to bring this in here so it's clear. So I'm virtualizing this one because it's connected to all of them. It's the highest degree one, and so now, and so those are correct. But then, obviously, missing here uh, this solution. This one has two cats, right? And this one has one cat, and this one has one cat, and this one has zero cats. So how is that then gonna work? Uh, that's confusing. The game graph is K1. We can perform the Oracle circuit without using control gate, control X gates. So hmm, the oracle for the edge connected to this virtual vertex can be replaced by a single qubit operation on the other vertex. Ah. Okay, so there's something else. Okay, so the fact that so I still should add a for the edges. So what is that for the edges connected to the virtual vertex? Uh, on the other vertex, in order to reduce the number of. So in order to eliminate this and double the social space, we choose the virtual vertex choose the virtual vertex whose state is the oracle or the edge connected. Okay, so in order to reduce the number of control gates in oracle part, it's effective to virtualize the highest degree vertex. For example, when the given graph is K14, we can perform the oracle circuit without using. Mm, so I am a bit lost right now. So implementation of the oracle circuit using subdivided phases for the star graph K14, all sub-oracles can be replaced with Z rotations by assigning the highest degree vertex to the virtual qubit. Let's try this then for a second. So we've got 4 in here and 5. So this would be the highest degree, 0. So I'm gonna move up here, and then we're gonna have like 4 more. Okay, and so we're just gonna, I guess, do that, which basically means adding a bunch more of these gates, and then copying these here and copying it here. So, and now, I mean, you've kind of got the same problem, don't you? I mean, you're basically saying, okay, that solution has one cat, 60 degrees, right? Same. Here you've got two cats. Uh, 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 uh. You've got two cats, but what if we paint that vertex from another? I don't get it. I'm just might be looking at it from the wrong perspective. So you're basically not. I feel so simple, but I'm just stuck with it. Because then it's already we're getting into the implementation of diffusion, but I'd love to understand that. So how does this work? So we've got the star graph. That's the one up here. This one. So let's try let's try to now let's try to maybe I was thinking to try to implement it the other way. But I mean that is a star graph as well, right? Um, the one here. So it's just that the vertex one is when you're virtualizing, and here you are virtualizing the vertex 0. Uh, but it's still hmm. In this case, what this is saying, it doesn't matter how you color 0. That's why you can virtualize it. No. Uh, so you're kind of fixing that, so to say. It's like you don't care how you virtualize it. I mean, it has. The thing is that hmm, the thing is that you're like, what about all the other solutions that have that vertex color 1? You don't have them in here, so you're missing solutions, aren't you? I mean, sure, this has two cats, three. So we're checking. Ah, wait a second. But it doesn't matter in this case because if it's a 1, so if you colored it, hmm, pa, 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 pa. Mhm, mhm. If you color it with so if you mark it 1, what is the difference, right? If it's connected to all of them anyway, you might as well just fix the color and then play with all the other combinations. But it feels like it's a waste of the superposition here. But you're reducing the. I mean, you literally have no control X gate, so you're reducing the. I guess you've got no errors in here. Um, hmm. So but is this then correct? I mean, let's say we're virtualizing. I just feel like it's. Don't feel completely good about it. This solution has two cats. This solution has two cats. This solution has three cats. Effectively, I mean, this is correct. Because effectively, if you, it's like you might as well just fix the color of one vertex. That seems to be the point of it. Fix the color of one vertex, um, and then just check whether the color in that case is different. And then if there's connections, like if this would not be, if there would still be, if there would still be some edge between, I don't know, this qubit and this qubit, you still need to do the double you still need to do the thing here where you kind of check whether it's like 0 1 and 1 0, right? Because you both possibilities still count. um, but effectively, if you pick the one that has the highest connectivity and then you virtualize it, you're reducing the amount of control X gates that you need, because you're fixing the color for that. uh, and it doesn't. I'm not sure whether it's so straightforward that that this, whether it's so straightforward that you can just do that and that this really works. I don't know. I think I'll stop right here, because at that point I'm just me asking the same question over and over again. Um, but it's still it's an interesting idea. But still, like if I go back to the example I was trying to do, right? Uh, but this one. So if I compare that with, so now I've virtualized that state in here. So if I compare, uh, so this one has 0 cats. This one has 1 cat. This one has 1 cat. And this one has 2 cats. That's correct. But because we're fixing the color to be 0, right? If the color would be 1, I mean, that's that solution is kind of the same like this one, isn't it? Because you're painting this in 2 colors, so that solution is the same like this one. Effectively, that solution is the same like this one, because you've got 1 cat here. You would also have 1 cat. Yeah. Okay. So you're saying in this, I mean, in that particular case where you have a star graph, like you can just you can just virtualize one, and then it completely, because you don't need the other half. Yeah. Okay. Yeah, kind of makes sense. It's a bit, for some reason, it was a bit unintuitive to grasp at the very beginning, and uh, and maybe I should just switch to the K14 example, because it seems to be the one that's used across the rest of the paper as well. We'll see. Okay, but this is it. I mean, if I would have another edge, um, between 0 and 2 here, right? Between 0 and 2, like I would still have to do a cross check between this qubit and this qubit in both ways. So I would have to still do the thing here with the, um, basically these and these, and so I still have to do that, because then it means that, for example, in this case there are 2 cats. In this case there are also 2 cats, and in this case there are 2 cats. Um, But couldn't I just then? I think that doesn't that. Uh, then I for that particular example I could approach it differently. But like okay, so I get it. So this is basically you can fix the color in the vertex of highest connectivity, so you kind of reduce the need uh, for implementing controlled X operations. Yeah, but still, that's a bit awkward because here there's also no control X operations. They are because you're approximating them, because you're approximating the circuit, and then you are adding the control X. The oracle of the edge connect to this virtual vertex is a single operation on the other vertex. Single qubit operation. Okay, but that's if it's a single qubit operation, then in the example, then there's something here that is not. There's something here that doesn't seem right. So I'll probably have to dig into this in the next video before moving forward because it doesn't. So figure 8 has control. It's not a single qubit. It's a controlled gate. It's a controlled gate in figure 8. But here, in order to reduce the number of control X gates in the oracle part, it's effective to virtualize the highest degree without using control X gates. As a single qubit, the oracle for the edge connected to this virtual vertex can be replaced by a single qubit operation, RZ, on the other vertex. I mean, yeah, it kind of makes sense because you're fixing the color. So if you're fixing the color to 0, you don't need to do that. That was the whole thing here. Is like why do you even do that? Like why do you even do X? Why do you even do that? You don't have to. If this is fixed to 0, you don't need to turn it into 1 to do a control. Then you just rotate. Then you just do these. Like so you do this actually. That will be. Let me get rid of this. So effectively, if you virtualize that qubit and you fix it to 0, shouldn't that just be enough? Yeah, that's enough. But then I think that figure is not. It's confusing. So because that's it, right? I mean, you've got here one cat, and two cats because you're virtualizing that. So effectively, you're fixing the color for that. Okay, I'll reach out with it because I think that's confusing. That's definitely confusing, and it's a really short, compact section too. And it's a bit because of the example seems to be wrong. So let's see. But I get it. Yeah, that makes sense. Now it makes sense. Now it's way more like that's way cheaper to do something like that, right? Because you don't need the two qubit gates. You don't need anything here. Just rotations because you're fixing the color here, and that gives you that. Yeah, unless I'm getting it totally wrong. I don't know. I'll see. I'll send out a feedback to Rod and then see what see what he says. Perfect. Thank you very much for sticking with this and looking forward to the next video.